So we're going to shift gears and we're going to work on establishing and using trigonometric identities. Before we flip to the next slide, I want to make sure that we know what we are talking about when we say identity in the context of mathematics. Identity. So when we have a statement like 3 plus 2 equals 5, where the left side is always equivalent to the right-hand side, even if it doesn't look the same, then the equality sign here is being used to establish an identity, an equivalence between two statements. So we're going to look at first establishing the reciprocal identities, which we kind of already have done, but we want to kind of drive this home formally. So we want to demonstrate that these are identities, and if they're identities, that means that they're always equal regardless the value we choose for theta. We want to understand, if we're working in the xy coordinate system, that our angle theta is going to be an angle in standard form, so measured with respect to the positive x-axis. And we've already demonstrated that if we have an ordered pair xy on the unit circle, the circle of radius 1, that ordered pair xy can also be described by taking the cosine of the angle and the sine of the angle. In other words, x and the cosine of theta on the unit circle are the same thing, and y and the sine of theta on the unit circle are the same thing. And then we want to look at the sine function. So the sine function, sine of theta, which we know is equal to y by what we've already established. But we have also, when we created the sine function or defined it, we also defined its reciprocal. We said, hey, if we have a side ratio y over 1, then the reciprocal of that 1 over y, we're going to give it a name. We're going to call it the cosecant function. But if y and sine are the same thing, then the cosecant function, because it's the reciprocal of the sine, is also 1 over the sine of theta. And we can kind of go through and make similar arguments for cosine and tangent as well, just establishing that these two things, even though they look different, they really are equivalent statements. So cosine of theta, we know it's equal to x on the unit circle. The reciprocal of x is 1 over x, and we gave the reciprocal of cosine a name. We said, hey, the reciprocal of cosine, we're going to name it the secant. But if x is the cosine, then this is the same as saying 1 over the cosine of theta. So these two statements, they look different, but they are equivalent. They are identities. And we could play the game one more time. We could say, hey, the tangent of theta has been defined to be y over x. And I can write this as an ugly complex fraction. I can make y over x over 1. So the reciprocal of y over x over 1 would be 1 over y over x. But the reciprocal of the tangent, which I just wrote here, we've defined that to be the cotangent function. And y over x in the denominator is the tangent of theta. So the cotangent of theta is 1 over the tangent of theta. So these are the reciprocal identities. And they could be, and notice that these could be manipulated into the other forms as well. So for example, this one, if we multiplied both sides by sine and then divided both sides by cosecant, we would see that, well, that was a dumb thing to say. I'm going to ignore that I was going to say that and go to the next slide. Pretend like I didn't say anything. Sometimes a person just needs to say stupid things. And I was about to do that. So the ratio identities are pretty straightforward. We continue to think about the fact that on the unit circle, that the ordered pair xy is the same as cosine theta, sine theta, as long as we're on the unit circle. So on the unit circle then, if we define the tangent of theta to be the ratio y over x, but we know that x is cosine and y is sine, then we can just make the replacement. We can replace y with sine theta, and we can replace x with cosine theta, which establishes this result. And then if we want to demonstrate that the tangent of theta is always the same as the secant of theta over the cosecant of theta, we can think about what does the sine equal. Well, on the previous slide we said, hey, the sine is the same as 1 over the cosecant of theta, all over the cosine is the same as 1 over the secant of theta. But if you have a division of two ratios, you can rewrite that as the product of the numerator times the reciprocal of the denominator, which is just equal to secant of theta over the cosecant of theta. So that establishes the second result as being an identity. It's equivalent to the tangent because I'm able to get to it through a series of equalities. And then the final one here says that the cotangent of theta is equal to cosine over sine, but that's easy to establish because we know that if the tangent is y over x, that the cotangent is x over y, and we know that on the unit circle x is the cosine, and we know that y is the sine of theta on the unit circle. So that establishes the ratio identities.